Hello friends, welcome back to the Electromagnetic Theory series. In the last worked example, we took a single point and wrote it in three different coordinate systems. Today we move up one step. We take a vector field and transform it from Cartesian into cylindrical and spherical coordinates. We will do two worked examples. The first one is almost a thought experiment, very simple, designed to show you what the transformation is actually doing. The second one is a standard textbook problem, Sadiku Example 2.2 style. Before we start plugging in numbers, let's see where the formulas come from. Remember, the cylindrical unit vector a rho points radially outward in the xy plane. In terms of Cartesian, a rho equals cosine phi times x hat plus sine phi times y hat. The tangential unit vector a phi equals minus sine phi times x hat plus cosine phi times y hat. And az is the same z hat. If our vector A has Cartesian components ax, ay, az, then its cylindrical components come from projecting A onto these new unit vectors. A rho equals a dot a rho equals ax cosine phi plus ay sine phi. A phi equals a dot a phi equals minus ax sine phi plus ay cosine phi. Az equals az. Three projections, that is all. We can write this as a 3x3 rotation matrix. The cylindrical components are the Cartesian ones rotated by phi around the z-axis. Example 1. Take the constant vector A equals 3x hat plus 4y hat. Evaluate it at the point Q, which sits on the positive y-axis. Q equals 0, 3, 0. We want A in cylindrical at Q. First we find phi at Q. X is 0, y is 3, so phi is 90 degrees. This is the critical part. At phi equals 90 degrees, cosine phi is 0 and sine phi is 1. So a rho equals 0 times x hat plus 1 times y hat, which is simply y hat. And a phi equals minus 1 times x hat plus 0 times y hat, which is minus x hat. So at this special point, a rho is pointing in the plus y direction and a phi is pointing in the minus x direction. You can literally see the rotation happen. Now project. A rho equals ax cosine phi plus ay sine phi equals 3 times 0 plus 4 times 1 equals 4. A phi equals minus ax sine phi plus ay cosine phi equals minus 3 times 1 plus 4 times 0 equals minus 3. Az is 0. So in cylindrical, A equals 4 a rho minus 3 a phi. The magnitude check. Square root of 16 plus 9 equals 5. Back in Cartesian, square root of 9 plus 16 also equals 5. Match. The vector didn't change. We just rewrote it in a different basis. Example 2. Now a real textbook problem. Take the vector field A equals y times x hat plus the quantity x plus z times y hat. The first thing to notice, ax and ay depend on position. Evaluate them at our familiar point p equals minus 2, 6, 3. At p, ax equals y equals 6. Ay equals x plus z equals minus 2 plus 3 equals 1. Az is 0. So at P, in Cartesian, A equals 6x hat plus 1y hat, 0 z hat. Now convert to cylindrical. At P, from the previous video, we already know rho is 2 root 10 and phi is 108.43 degrees. So cosine phi equals minus 1 over root 10 and sine phi equals 3 over root 10. A rho equals ax cosine phi plus ay sine phi equals 6 times minus 1 over root 10 plus 1 times 3 over root 10 equals minus 3 over root 10, about minus 0.95. A phi equals minus ax sine phi plus ay cosine phi equals minus 6 times 3 over root 10 plus 1 times minus 1 over root 10 equals minus 19 over root 10, about minus 6.01. AZ stays 0. Let's check the magnitude. A rho squared is 9 over 10, a phi squared is 361 over 10, sum is 370 over 10, which is 37. And in Cartesian, the magnitude squared was also 37, 36 plus 1. They agree. Now spherical at the same point P. From the previous video, r is 7, theta is 64.62 degrees, so cosine theta is 3 over 7 and sine theta is 2 root 10 over 7. Phi is the same phi as in cylindrical, 108.43 degrees. The spherical transformation matrix involves 3 sines and cosines because the unit vectors AR, A theta, A phi each have a different orientation. AR equals AX sine theta cosine phi plus AY sine theta sine phi plus AZ cosine theta. Plug in 6 times 2 root 10 over 7 times minus 1 over root 10 plus 1 times 2 root 10 over 7 times 3 over root 10 plus 0. The root 10s cancel nicely. That gives 6 times minus 2 over 7, which is minus 12 over 7, plus 1 times 6 over 7, total minus 6 over 7, about minus 0.86. A theta equals AX cosine theta cosine phi plus AY cosine theta sine phi minus AZ sine theta. Plug in 6 times 3 over 7 times minus 1 over root 10 plus 1 times 3 over 7 times 3 over root 10 minus 0. That is minus 18 plus 9 all over 7 root 10 equals minus 9 over 7 root 10, about minus 0.41. A phi equals minus AX sine phi plus AY cosine phi. Notice this is exactly the same expression we had in cylindrical, so A phi is the same, minus 19 over root 10, about minus 6.01. Now a sanity check that any engineer will love. The magnitude of a vector is coordinate-free. It should be the same in all 3 systems. In Cartesian, 36 plus 1 plus 0 equals 37. In cylindrical, 9 tenths plus 361 tenths plus 0 equals 370 tenths equals 37. In spherical, 36 over 49 plus 81 over 490 plus 361 over 10. Common denominator 490 gives 360 plus 81 plus 18,369 equals 37. All 3 match exactly. That is the physical meaning of a coordinate transformation. You have rotated the viewing angle, but the thing itself has not changed. Quick recap. The cylindrical transformation is a rotation by phi around the z-axis. A rho equals ax cos phi plus ay sin phi. A phi equals minus ax sin phi plus ay cos phi. For spherical, the matrix is bigger, but the idea is the same. Project the Cartesian components onto the new unit vectors. Always check the magnitude is invariant. If it isn't, you made an algebra mistake. In the next video, we will use these same transformations on real vector fields with differential elements and start computing flux integrals. See you then!